Okay, welcome everybody. Today's seminar is part of the project Functional Renormalization Group Methods in Quantum and Statistical Physics, which is a project funded by ACRI, Associazione Casse di Risparmio Italiane, under the Young Investigator Training Program 2018, which enabled the one-month visit of a group of young researchers in various locations in Italy. In particular, credit goes to the local host, which are INFN Sezione di Catania and INAF Catania, which are the local nodes that are taking care of of three researchers of this group that are visiting Catania in these months. Now, the goal of the seminar is spreading of knowledge of the functional renormalization group method, and among both researchers and students in here in the local host institution. So it will be at an introductory level, and the speaker today is Dr. Lesław Rachwał, who got his PhD in 2013 at CISA under the supervision of Roberto Percacci. Then he went through postdoc experience, first at Fudan University in Shanghai, China, then at the University of Brasilia in Brazil, and finally, right now, he has a postdoc position in Prague at the Czech Technical University, and he is now here and will talk on an introduction on quantum gravity. So, please.
Okay. Thank you very much. So first I wanted to thank organizers, Alfio and Daria, for inviting me here. And yeah, it's always a great pleasure to be part of this program. So again, I want to thank INFN and ACRI who give me the money. And that's why I could come here. So that's an important thing. We have to also always advertise our sponsors. So these are our sponsors. So now I will talk something about physics, but since I didn't know what could be the audience, I tried to be quite general, and this will not be technical. It will rather be, you will see only a few formulas, more words, and you see there are not so many signs. So, you've seen that picture. Actually, there is this guy at the department who creates the website with announcement and with all the events. Luckily, he almost got the same picture that I got. But there was no any coincidence, and there was no any agreement which picture we had to take. But this one is almost very similar. So you may imagine, what is this topic that I'm going to talk about? It's a very ephemeral topic, and this is supposed to be some space-time, but you see there are a lot of strange things going on. There are some blue curves, violet curves, ultraviolet, but there is also some rings, some spherical symmetry, some, you can say it's a deformed space-time because it's slightly curved, but you don't know, there are a lot of things happening. There's something from the vacuum, something here, where is the black hole, you don't know. This could be the good picture, and you see the same one, almost the same one was on this website when my seminar was announced. So okay, this is maybe a picture, there will be also other. So let's start with something that you can, I believe everyone knows, and then this is like introduction, so you can be just first year student of physics. So first we can say that it's actually this Bronstein cube. Bronstein was one of the first guys who spoke about quantum gravity, so he invented this cube. Although you may think this is too little dimension because they are just three, you may maybe need more dimension, but let's concentrate on just 3 dimension. So each of the dimension corresponds to one coupling or one parameter of the physical field that you can turn on. And you see you have the velocity of light, you have gravitational constant, and you have Planck constant. These 3 fundamental constants of nature, but as I said, they are not the only fundamental constant as we know, because you see in this corner of the blackboard, you have also other, like for example Boltzmann constant, or the permittivity of the vacuum. So you can also turn other direction, then you can ask what happens in this other direction. For example, when you turn on Boltzmann constant, you may want to say how this picture, how this cube extends when I have also thermal effects, or something like that. So, if you don't know about this Bronstein cube, basically you start from here when you are very okay and confident with Newtonian mechanics. You don't have any relativistic effect, any quantum effects, no gravitation, and you try to explore, because gradually you discover that there is something. When I go to higher velocity, there is special relativity. So I turn on C, and when I got here, you can turn on H bar when you say there is quantum mechanics. It's not Newtonian mechanics which describes the world. When you turn on just G, you get Newtonian gravitation, because still there is no velocity of light, turn on, and there is no Planck constant. But if you know just that you can move in all these three directions, you can ask, okay, what will happen if I move not just in one, but I will try to go maybe what happens on the diameter of the cube. And then what is in the diameter of the cube is actually the point when you have turned on everything. So you have both gravitation, relativistic gravitation, and also quantum. And how you can get there? You can get there by following some path from one of the corner of this cube, from one of the vertex. You can, for example, go from here. You can just turn on relativity. Now you get general relativity. Or you can go from special relativity. You turn on H bar. You go to quantum field theory. And if you just turn on everything, you get there. Now you can ask, okay, why I didn't go here? Maybe I just, you see, I tried with Newtonian mechanics, and then I put gravity, and I don't have relativistic things. But you can see, it's a funny story, that actually this theory doesn't make sense. So, like all the others, they make sense in their domain of applicability, because you can, for example, say special relativity is when I don't have gravity, I don't have quantum mechanics, and then it must be theory which is exact to its accuracy. This theory is pathological, it has some problem. So that's why I cannot go to this corner. But the final point that I want to go is quantum gravity, which is when everything is turned on. So this was a very basic discussion of the Bronstein cube. I can tell you that actually the story is funny, that every student know what was first, quantum or relativistic physics. It happens that relativity was first. So that's why we followed this route. If instead we discovered quantum mechanics before relativity, before special relativity, we could come here. And when we discover something is wrong with the theory, this would call us, okay, we have to recover and we have to rethink our relativity, our physics without our classical physics. But this is not the case. Actually, the historical path was first relativity, later quantum mechanics. So now let me say something about this point. So there is this hypothetic theory which describes the phenomena, physical phenomena, which happens when H is not vanishing, which has its meaning, G has its meaning, also C has its meaning. Although typically you can see that if I choose the units convention which are here, I can set to 1. I can set to 1 almost everything except G. You can ask why I didn't set G to 1, because the topic of the lecture, it's a randomization group. So everything will run, but G, everything except it is set to 1 will run. So G will run. So that's why I don't want to set it to 1. That's why it must be not set to 1. It must be kept as a general thing, and then you can see how are the randomization group phenomena related to this. So let's just do some textbook calculation. Again, first year physics. You can take the value of Newton constant, because this is the G that we use, and this is in SI units. Okay, you see this is this, and then you can derive some quantities which should correspond to what happens in this regime. So how we do this? We just combine, and then we want the dimension to cancel, or to give us the dimension of Planck, of mass, Planck energy, and so on and so on. So you can, for example, everyone I think is familiar with this, because this describes how the objects fall. Yes? But you can construct these quantities which somehow describes the regime of quantum gravity, and then you can compare to our everyday life, and then you see how crazy it is. Because, for example, you can compare the mass. Okay, the mass is not so big. It's like mass of one bacterium. So you may think, okay, what is quantum gravity? It's a theory of bacteria. But, and you see, we will go more crazy then. This was mass. But we can do something else. We can compute energy. So this is the combination for energy. Now the energy is slightly bigger. You can compare, and then you can ask, where do I see this energy? And I can tell you, if you take your car, I mean for 4-person or 5-person, and you ask how much is the energy of fuel stored in the tank, this is a typical energy. I mean the chemical one. If you ask at the oil station to fill your tank fully, this is more or less that energy that you feel. So okay, it's not a fear of bacteria, it's a fear of energy that we typically have in our cars. Okay, something else? Yes, now let's compute length. And this is something that we never really see in our life. Because this length is very small. It's not atomic physics, it's even smaller than that. It's not nuclear physics, quarks and everything are very, very big objects compared to the quantum. So this tells us that already this is more crazy than just a theory of bacteria. It's a theory that we have to put this energy that we have in a car tank in the region which characteristic length is of this size. And this makes it really complicated. Or if you want to go to something other extreme regimes, you can compute what's the time. And this is not the time that you can even meet in the most accurate experiments of optics when they go with attoseconds laser and so on when they are transition between atoms. It's again very, very small time. So you have to put this energy in a volume which is basically cube of this length, and you also have to do it in a time which is so small. So you don't see these quantities in everyday life. And then you can say, okay, if I turn on this Boltzmann constant, and I also can do the same game with Boltzmann constant, what you get is the expression here in Kelvins. And again, it's a temperature you don't even meet in the center of the sun. Probably this temperature question the applicability of that you can speak about temperature, because temperature is effective phenomenon, statistical description of many degrees of freedom, and here we don't have any example of really matter that can express so high temperature, because maybe even the temperature cannot exist. But imagine that you can put these things all together, and then if you put these things like that, then you are in the regime of quantum gravity, and to describe this phenomena you have to use quantum gravity theory. So this was just a sketch which kind of regime of physical theories we are. And now let me try to say why we have to look for this theory. Of course we can go this 3 steps way on the diameter of the Bronstein cube, but also we can have some formal or more theoretical arguments why we need quantum gravity. So first we know that we said that quantum mechanics and Einstein gravity were 2 successful theories. They were invented at the beginning of 20th century, and if we think that the world is kind of unique and it permits for uniform description, we should find the one which merges the two. It's not that kind of schizophrenic that one day I think the world is quantum, another day I think the world is relativistic, and then on Sunday I say I go to church. No, it's not like that. So you have to find look, this was an old joke by Heisenberg about waves and particles, and you see that's why there is the Sunday. So we cannot do like that. We look for something which will unify together things. So another point of the story is that you see when you can write there, for example, the Einstein equation, which I think some one of you may have looked at, and then you have the one side which is related to the space-time, but the other side is related to the matter. And what is on this matter side? We know that this matter, thanks to theories of matter composition, we know that this is quantum, because there's all standard model and maybe also something beyond is here. And this thing is quantum. So you see, if this is quantum, then also that must be quantum. Somehow I will show you how to write it, because I will have later some little proof of the theorem of the quantization. But one thing you can already understand here, that if the one side is quantum, so it is not just a classical it's not just classical function is operator, then also the other must be operator. And basically quantization is changing from classical functions to operators. So you will also have to make operator on this. But it's more complicated than just work. So these are some kind of theoretical arguments. You can also invent some problems which are already in the classical Einstein theory, so in just general relativity. For example, you have this problem space-time singularities. There are some very powerful theorems due to Hawking and Penrose that whatever is the symmetry of the system, if you have concentrated matter enough, then inevitably you create something like end of the predictability of the standard GR, and this is typically called the space-time singularity. So of course, this kind of objects, they put in question your possibility to do prediction further because you meet singularity, and then you have to put a new time initial conditions. So this is not a good thing if you think about deterministic physics, because deterministic physics tells you start with your initial conditions at one moment, and then if the physics is okay, then it will tell you what will happen whatever time in the future. But you meet singularity, and there's a problem. This is one point. Another point, you may maybe have heard about the problem of the self-radiating electron, which was the problem for classical electrodynamics. There is a similar problem with gravity, because if the particle is moving under the influence of gravitational field, it will also emit gravitational waves. Very small. For example, Jupiter doesn't emit much of the gravitational wave in its motion around the sun, but you can compute. And then this emission of the gravitational wave will influence the trajectory. So this is a problem kind of self-coupled, and again, like the problem of self-radiating electron, here you also need some resolution. Actually, we know that resolution, which was in the case of electrodynamics, came because of quantum electrodynamics. So the same here. If you want to resolve this problem, you have to go to quantum gravity. And this is basically also this last point, that the special situation happens not really for Jupiter, because the Jupiter is a very big object. This you discover by just comparing its Compton wavelength with its Schwarzschild ray. But you can think that maybe there are some objects in the universe for which this relation between the two radii is not so different. And then the situation and the question arises, what happens there? And you see, we are just describing gravity, but as I said, there is also this matter side. So we have to think also about what is going on with these other interactions for which we have quite successful quantum field theories, because we have quantum field theory standard model, which we have a lot of particles, and then particle physics is still in a good shape. But now you see there is a gravity, and then you can think, okay, how to couple this to that, and then how to make a unification of the two, because there is maybe the old idea, which was in old time even by Einstein and also others, that maybe you want to unify all fundamental interactions, not just particle physics alone and gravity alone. Maybe you want to find something that encompasses both of them. Fundamental interactions, and so electroweak and strong, and also gravitational. So this is something of the theoretical size. Now let me go into this little theorem that I will try better to advocate, not just to prove, that you see, in our universe we have some very peculiar situation, because the size of it is not infinite. At least that's what cosmology says. The size is quite big number, but of this magnitude, 10 to the 27 meters. And now you can think, okay, I have this universe, and then I can count how many degrees of freedom are there in this observable universe. Of course, what is beyond observable, we don't know. And then you get this number, 10 to the 80. And then you can see, okay, this number is a finite, but you know, for the frequent interpretation of quantum mechanics, you would like to have n equal infinity, but you don't have. So you have finitely many degrees of freedom, and actually there is some theorem that I will show on the next slide, that when you have two systems, that one is classical and the other is quantum, and this quantum has finitely many degrees of freedom, and this is the case for our universe, then if one is quantum and the other is classical, you cannot describe consistently the evolution of the total system. To make the consistent evolution of the total system, you must also say that this first one cannot be classical, must be quantized. So at the end you have interactions between quantum system with finitely many degrees of freedom and another quantum system. So yeah, let me show this. So this is basically the problem of action back reaction that we have to take in gravity. When the system A, as I said, let's say that this is that one with matter. So this is, we know that there are some quantum degrees of freedom, and then we can say that in our universe there are big number of them, but finitely many. Then the gravity acts on it, but also this system back reacted on gravity. And if you want to have the whole evolution consistently, since here you have operators, here you have quantum mechanics, and also there you have operators, so also there you have to go to quantum field theory. This is basically what I said now. I told you have to put operator character on everything. So basically these arrows, they describe the interactions, but now they have to be both ways, so they have to be action and back reaction. So that's why we have the, basically, you can say that the total Hamiltonian which describes the system is now the sum of the separate Hamiltonian in each system plus the interaction, and the interaction can depend here on the variables, on the operators in each of the sector. So the conclusion is that basically the system V must be quantized too, and then you cannot keep the system be classical, it must be quantum. And of course here is important this fact that I told you there are finitely many degrees of freedom in our universe. Because if you have some classical fields, theoretically classical, so smooth configurations of space-time, so you can have even electric field, then in principle you can still keep it as external source, and then it works like this thermal reservoir, so it can accept whatever changes, because it's so big that whatever you do in the small system, the big system doesn't back react. So, but this is not the case in our universe. In our universe we have this number of degrees of freedom. So now let me show some prehistory of research of quantum gravity. So see, this prehistory I said because it stopped, I mean this part of development stopped something in the 50s, but you can read already they are a quite famous name on these lists. And yeah, let me just say something. That, for example, you see, it was, although we heard many times that Einstein was one of the critics of quantum mechanics, he already knew that, yes, we have to kind of compare the two things, that gravitational field I discovered was very nice, the theory is very beautiful, but still I have to incorporate quantum methods. How? I don't know, that's what he said, but they must be incorporated. It's not that he forgot about his development with the photon. No, he also thought about gravity. And then some people say, for example, like the Russian Blokintsev and Galperin, they said that basically if you take this field and you linearize, you do Pauli quantization, so you just do operator quantization of the linearized fields, you write the creation annihilation operator, then you get something which is analog of the photon, but then these guys, they call it, okay, let's call it graviton. And then the production of particles started, and also, you know, there are a lot of Italian developments of particles. I will show you how the names go. So this is how the kind of name was born, because they said, okay, there's photon, so why not let it be graviton? So you maybe heard that, you see, in the 30s, there were not so many particles discovered because they didn't know whether there's proton or neutron. Neutron was only discovered in 22. But already in 44, they hypothesized, let's call it graviton. So this particle is also quite old, although of course it's hypothetical. And then here we have also other people on the list. There's the same Bronstein from the cube. When he said that there's some background independence need for the formulation, because already Einstein equations, they were background independent. And there were also some people saying that, okay, now we have quantum effects, so we cannot just use the standard space-time, we have to include some quantum effects. And then, yes, this means that the classical notion of space-time has to be modified, but still, we don't know really how. So they were just kind of signs that, yeah, we have to do this, but how to get there, we didn't know. And then some people already started seeing some important features, like Heisenberg. He said that, look, you have this G Newton. If you consider it as a coupling in terms of high energy units, there is something strange because it's negative dimension. Not all other couplings, they had a negative dimension because, for example, electric charge is dimensionless. You can say it's something like the Fermi constant, or Fermi, or interaction between four fermions, but here was already something, I would say, very profound, discovered by Heisenberg, I mean pronounced by Heisenberg, that look, this coupling is negative dimensionality, so there could be some problem. And then later we will see, and there are various resolution of this related to basically randomization group. And the fact that this dimensionality is negative makes the randomization group for gravity quite special and quite not very intuitive. So of course, there was one part of the development related to this background independence, and then some people basically work on that, and then already in this time, like just after the Second World War, there was some splitting. You can just analyze these 2 points. They were splitting because the people decided either to be on canonical side, so use canonical transformations and write everything in this way, or do covariant quantization. So this is a question that, okay, we do not put it in so much contradiction classical mechanics. Do you choose Lagrangian or Hamiltonian? We know that we can describe the system in both ways. It depends what we want to do. But here is a kind of like, at least in the 50s or in the 60s, it was a war. You are covariant or you are canonical. And you see, they were completely different approaches. And since that splitting started in the 60s, there is still not a kind of merging saying that, look, they are the same side of the same, or they are different side of the same coin. No, it's very difficult to show, even for young means, it's very difficult to show that only in some gauges it was done that canonical quantization is equivalent to the covariant one. But for gravity is even much more complicated. So this is the prehistory. Now let me say something with the equation that at the beginning everyone will agree, but then later I will show how we disagree. So let me just first say that what I want to talk about here is that you see we have a gravity and we have quantum mechanics, and then I want to say that the relation between the two is that quantum mechanics requires modification of gravity. But there are also people who say the other way, say that no, is that gravity requires modification of quantum mechanics. And then you see, I prefer to quantize gravity, not to gravitize quantum mechanics. But you can also find papers about gravitization of quantum mechanics. So let's quantize gravity. So this is the equation that basically everyone should agree. This is the time-dependent Schrödinger equation.
What is time?
Sorry?
What is time?
Yes, this is one of the questions. So you will see that out of the objects that we have to use to build this equation, there's only one which is that everyone agrees what it is. I leave you for a puzzle, what is this? So you can ask, what's time? What is the state here? Because we have the evolution of some state. So this is a question how the Hilbert space is made of. Or, if you just consider pure gravitational theory, then you have the Hamiltonian, which is due to constraint is always zero. So what does it mean that here is zero? So there is no evolution, no? Or what is the time? Is it a coordinate, or whether it exists? Some people say that due to the evolution properties and Cauchy surfaces in standard GR, time is not a thing. You can just reparameterize it, so it doesn't exist. So why I put it here and also here? Or maybe it's quantized, or do we quantize coordinates or not? This is a question. And another questions come along the way, because you see we have only partial derivatives, but we have the general activities about the general covariance. Why here we don't have this? And what with the Lorentz symmetry? Why is distinguished? Why I have only time? What with space? Where is the field? Why this is like that? So you see, there are many questions, and different people, they answer these questions different way. But this is the equation that I believe there is no any paper which says I do quantum gravity, I don't like this equation. No, everyone likes this equation, but everyone has different interpretation of the things which are in. So now you know what was not kind of contentious here. It was this thing here. Everyone agrees about it. So let me just put you are young, so okay, most of you are young. So you are maybe at the beginning, and then you may think what to do. So let me put some warning, because you see, maybe it's risky to spend your future doing some kind of crazy things, like so many people have so many opinions and there is no consensus, and then you don't know what to do. So sure, it's a very challenging topic, because you see, this is like the end of the cube, the corner that no one has ever gone, and then you want to be the first to reach this corner and say, okay, now I understand the world and how is the mechanics of it. But you see, there are these technical difficulties that are very enormous. It's more complicated than just the theories that we use to describe standard model. It's more complicated because the gravity is, in some sense, square of the gauge theories, and here this problem are already present on the level of gauge theories. Now they are twice as more complicated in some exponential scale. And they are different approaches, I told you. They are different approaches because they decide to answer these questions in a different way. I will, next slides, I will try to show you how these approaches differ, and list some of them. You will see the list, and then you can ask some question if you are interested in one of them. moreover, since you see we are theoreticians, and here I describe some theory, this requires quite advanced mathematical techniques. Sometimes we are not so happy that mathematicians discover the mathematics that is needed here. Sometimes we, as a physicist, we have to discover mathematics. And this is the kind of story that maybe it was not in the past like that. For example, Newton used his calculus, and when he was just using the things given to describe mechanics, Newtonian mechanics. Here, maybe we have to invent or wait for mathematicians to find solutions to our problem. But besides the theoretical problem, look, there is this things about the experiments observations, because most of the time in physics, the condition for the progress was that there was experiment and theory, and then experiment and theory. But here the part of experiment observations is missing. And is missing, you can say why. Because on one side you have this M Planck, which if you write in the particle physics units and compare to the masses of elementary particles, is very, very huge. So if you said something which is very, very far from the reach of your accelerator experiments of particle physics, then you cannot tell anything right now in terms of experiments. Or if you want to do some space-time physics, and then you just look, for example, in the sky, or want to do some satellite experiment, you see that now this length of the Planck is very, very small. So again, it's something that is beyond your reach, and maybe you have to wait very long time or do something very precise. But generally, you can say that there are no clear experiments or clear observations that will single out this is a correct way to go, or this is a correct approach to study the problems of quantum gravity. So that's why it's almost a purely theoretical exercise. So you see, we almost do this kind of things that there's no mathematics discovered yet, and we are trying to put the theories still as far as we can along the roads that we used to go in the theoretical physics. But still, it's a very interesting problem. So let me just maybe ask you. See, there were the slides with the Planck units. You can ask, is there something else in this list? Yes, you can also write Planck charge. If you play with the H bar, C, you don't need Newton, but you need the permittivity, so electric charge. And then actually electric charge is not so crazy, because electric charge, if you compare in the units that you use to measure the charge of electron, it's not so far. It's actually some electric charge divided by 4 pi. So you see, Planck charge is not so crazy Planck like all other things. But all other things here, they were crazy, at least to everyday life. But you can compute Planck charge, and this is something there. So let me just say a few problems, which maybe there is a long list of problems that quantum gravity will try to solve. But I can say that one which, the two which are maybe one of the most urgent problems is that there is this problem of infinities. That classical GR tells you that they are inevitable, so we'd like to make a theory to go through it. And also this problem of singularities that you also meet when you do some computation in quantum field theory. Then you have here these things in gray, so you cannot read so well. Why? Because you see, this is the list, additional one. You may want to take some parts of it, or maybe you can say, I don't care. And then you see, because maybe it's just, you are maybe simple-minded person, you say, okay, I just want quantum theory, I don't want fundamental interactions. Okay, there are some matter, standard model, there are 20 particles, who cares? I just care about one gravity. So, this is possibility. It's not that it must be fully included if you want to solve the problem of quantum gravity. Then you see, you can entertain yourself with reading. So, for example, try to find the reason for the inertial gravitational masses, or to say what's the structure of the space-time. Again, you can say, maybe I care or not about the standard model. Do I want to embed it in quantum gravity? You see, there is also some lot of approaches of people who say, standard model has problems, but when you couple it to quantum gravity, maybe this problem will be solved. But this is putting a lot of bargain on quantum gravity, because quantum gravity now should be solution of everything. So maybe it's too, it's not very modest approach to say that all the problems of particle physics they will be solved by quantum gravity. Maybe it's not. So that's why it's in gray. Just in the quantum gravitational part, we have, you probably have heard about the black holes, and then there is information loss paradox, so this is maybe something that should be solved in the good theory. Or you can say, okay, there's also the value of the cosmological constant that I would like to also to explain quantum gravity, but maybe not, maybe it's something, again, external, just I'm modest, I want to think with graviton. So this is, of course, the list of goals. You go more and more unmodest, and then at the end you can say, okay, I want to explain everything in theoretical physics, and then this is the part of the, let's say, a bit funny development that you see people were guiding this way, and then you said, okay, now we are, some people said sometime, that we are almost on the verge of constructing this theory of everything, but you see, that's why it's this question mark, because I would say it's more smiling thing now. So there is another picture that I found. Of course, it's not this artistic view. You can say there's some singularity here, more like this singularity of the black hole. Again, I don't know what are these lines. They do not look like Judith. Or, you see, there are not only the theoretical problems, there is also this problem that we look at the sky and then we can try to build a theory, and then the theory tells us something strange. That when we look at our universe, we actually think that we know this 4% only. The other 96 is dark. So dark means that we don't know what it is. But then we can basically either say that this is, they have slightly different features, like slightly different properties. There is some part which is dark matter, which we can detect gravitationally. It has to do with the rotation curves of galaxies. And this is, you see, it's dark, but it's, let's say, very dark blue. But there is this completely black dark, which we completely don't know what it is. And that's actually the biggest part out of this sector. So it's 74%. And yeah, it would be good if you want to apply this quantum gravity to some physical system, it would be good to explain what is this part and how it comes from. So let me now, we have still some 20 minutes, let me now describe some approaches. You will see there are many of them. So first you can ask, okay, which quantization method? As I said, there was this war between covariant and canonical, and this was like between Lagrangian quantum field theory or Hamiltonian quantum field theory. Before what I showed you, there was this paper by Klein who applied the Pauli quantization, so it was just linearized theory, and then we just had creation and annihilation operators. But then already for the Russians, this gives rise to the possibility of calling these excitations a graviton. So you could say this was also some, but only on the linearized level. So this is one question, which method to use, but then another question, what to quantize. Because if we quantize point-like particles, then we basically do some QFT of gravity. Like we say that in QED we quantize point-like electron, point-like photon, and then we end up with QFT of electromagnetism, which is QED. This is one option, but maybe we should not be only concerned and focused on the point-like particles. Maybe we should think they are more fuzzy, or maybe somehow dual. So you can say, okay, point-like particles, they are zero dimension. Let's increase dimension step by step. So you can go to links, and then also to holonomics, which are basically dual to links, so they are like fluxes. And then what you quantize this way is basically the Wilson loops, and then you get something which is loop quantum gravity. So it's not a theory of point-like particles, it's a theory of quantum loops, which are basically the loops with the flux, or they are dual to links. Or you can say, okay, I was still from zero dimensional, I go one dimension more, I found some objects which are one dimensional and they are vibrating and they are called strings. So then here you open a lot of Pandora box, because there is a big theory, big landscape of theories of string theory, but then you also have to typically add supersymmetry, so that's why there is super here. Or you can go even one dimension more, or more than one. So not just one dimension, but two and higher dimensional objects, and then you get membranes. So that's why you get M theory, which is like inverse of W. Which is, you can know the story. So basically you can decide what to quantize, and then you see, depends if you are zero dimensional, one dimensional, or higher dimensional. This is the question, the same emanation of the same question, what are the true degrees of freedom of the quantum gravity? Because one of the questions we can have is, yes, what is really that? Whether they have some atomic structure or not, whether they are extended objects or they are fuzzy or they are just point like photons and electrons. This we don't know. Another question you can ask, what is the symmetry? Because of course a lot of interactions that we have in standard model, we know how to write them because first we discover this is a symmetry. For example, there is isospin symmetry or there is some gauge symmetry of SU2 or SU3. So you can ask what is the symmetry if we have gravity. And then there is also an option here of various lists of symmetries. You see they are not all equivalent. So just in GR we have diffeomorphism. And then you can say, okay, I just want to use this as a symmetry. But there is also a different version. You can say, okay, I know that my theory on flat spacetime, it was invariant with respect to Poincare transformation, which is a group different from diffeomorphism because it's SO13, this semi-direct product with the translation. And then you can say, okay, I can do something like quantum gravity, but now I have to do gauge symmetry of the Poincare group, which is a different group. Or you can say, no, I want to be supersymmetric, that's why I also put super in the game, and that's why you get super gravity, super string when you always put super. Or another symmetry you add to the game, conformal. Conformal symmetry, which tells you how to rescale the things, and that the scaling is basically innocent operation on your theory. And then you also get something which is conformal gravity on conformal supergravity. I think they didn't get to the conformal superstring theory, like to put everything. But because it's, you see, too many symmetries, also you get crazy. Or you can say, no, even on the classical level I had some invariance with respect to general affine symmetry, which is not here SO13 but GL, so general linear transformation. So see, now you have a group of symmetries, you can choose which one you want. Another question you have to choose, and when you see, if you basically to start doing quantum gravity, you have to take your attitude to every of this question. And then if you set this, that, then you basically in your corner, and when you start doing computation, then yes, you have tremendous difficulties. But first you have to answer this question. So you see, it's a kind of first step. You can ask, so what is more important, field theory or quantum mechanics? Although you see the first slide, one of the first slides, I told you that there is finitely many degrees of freedom in our universe. So this would say that maybe quantum mechanics. But from the computational point of view, maybe field theory is better. So you can have quantum field theory of gravity if you are on the side of field theory, or another side, you can have quantum mechanics, and then, for example, most of the string theory is formulated as quantum mechanics. So you see either field theory or quantum mechanics, because if you want to have the things together, like quantum, string, field theory, there are more question marks here. So basically, this thing has a lot of problems and a lot of inconsistencies. So that's why you have to choose what you want, field theory or quantum mechanics. Now, let's say that we choose quantum field theory. And then you can say, okay, so now I want to study some phenomena of the quantum field theory type. One of them is synchronization group flow. And then you can maybe want to know what happens in the UV, because one of this problem that I showed you about this infinities, this captures the behavior of the theory at the very high energy. So this is ultraviolet limit of the theory. And then you can ask, how is the flow going towards the UV, towards this limit? And when you have option, depends on your model of quantum gravity, studied in a quantum field theory framework, you can have it either this is asymptotically free in some couplings, or that this is maybe asymptotically safe. And this is some part of the program that we are here, because actually to tell something more about this condition for the asymptotic safety, we use the functional RG. And let me tell you that yes, this very interesting option of asymptotic safety is when you have fixed point of the RG. Fixed point means that there is no flow. So okay, I said that there is a flow, but actually you are happy when there is no flow and everything stops. So no Poincare. And this you want in the UV, but this is not only the condition. You also have to have the number of your parameters that describes the situation to be finite, because of course if you have infinitely many, then you didn't gain too much. So these are the conditions for asymptotic safety, that you have to stop the flow and you want to have finitely many parameters. If you stop the flow not in a point where you have trivial values of the couplings, then you are not asymptotically free. That's why you have this notion of asymptotic freedom. You can say, okay, if I take some models of quantum gravity, then even before the normalization, you can ask what happens with these infinities, whether I can absorb them or not. So this is the the famous theoretical question of renormalizability, and then you can say, for example, Einstein-Hilbert gravity is non-renormalizable. This is one of the problems that basically tells you so why to start with Einstein-Hilbert. You can try to go to some models in which the control over the perturbative divergences is better, and then you can have some renormalizable theories. Typically they come with higher derivatives, so that's price to pay. You can have even models when you have very good control, they are super normalizable, or even such that you don't have divergences. So let me say that, you see, old Paul Dirac was very confused about all this renormalization program in QED, and when he said, no, I invented my Dirac equation and I wanted it to be without divergences. So he was still thinking till the end of his years that the theory of quantum electrodynamics should not consist, the renormalization should not be part of it. He should have a theory when there are completely no divergences. And maybe there is some possibility to find such theory when you have in quantum gravity framework, when you don't have any UV divergences. So this is something like Dirac would probably like to see. Or another question that we have in this quantum field theory framework is whether it's a more fundamental or effective quantum gravity. Because if you see, if we start doing these things with the quantum field theory, then typically we pick up some action and then we say it's fundamental. But maybe we should only use some effective quantum gravity description. I will go also with some slides later. So yes, these are basically what I said, that to start doing these things with quantum field theory, we have to pick up some action. Yes. This is one of the type. If you have just Einstein-Hilbert, you can just have Ricci scalar, and then this is the action that you use also for classical physics to describe the dynamics. But you can say I want some modification of the action principle, and then it means that I have to put something else here, and then you can say that they are maybe IR or maybe UV modifications, or maybe they are non-local. So, of course, now in these years there's a lot of modifications and people invent a lot of different things, how they can modify the action principle. So they can add terms which are, for example, higher in curvature. Here they are quadratic, and actually this, for derivative theory, is renormalizable. So there is a good thing. Of course, there are also other things which happen to be bad. But then you can add other things like just arbitrary functions of the Ricci scalar, of the torsion, of whatever things, and then, yes, you can have a lot of things. But let me just show you which kind of new geometric elements you can have. Because in GR we have just metric tensor G mu. But differential geometric tensor is not maybe the only thing you can have. Because you can have maybe dynamical torsion, which is the antisymmetric part of the connection. So you can have this in the game. At the low energies and in our microscopic world we have not seen it, but maybe it's there. Or maybe we have this thing which is non-metricity, which is actually derivative, covariant derivative of the metric tensor. This may also be non-zero. We can have everything in this independent connection, and then this gives rise to this affine metric theories that I told you, the general inner group. But what could be the effect of this? Also that there could be some new particles in the spectrum. And now here you see, if you're Italian, you can enjoy a lot, because see, all these namings of particles comes because of Italians. So, of course, on is the old thing, but then gravitino, gravitello, graviphoton, you see, they are very Italian. And also dilatum, dilatino. See, everything could be there. So, and there is also radium, there is probably no radino, because I don't know how to say it, But you can have these particles just beside the graviton, which was in 34. Now you can have also, in particular model, if you choose, you can have also this gravitello, graviphoton, you see a lot. And not just one. You can typically have many of them because they are in some multiplex, supersymmetry. So you can have these new particles, but okay, we can also have new fields, because we have this metric tensor field G mu nu, but we can add some scalar fields. Why not? Gravity doesn't tell you that this is only metric. So we can have this type of theories which are Brunson-Deakin, Starobinski, or we can add vector. Then we have something like magnetism, electromagnetism, but here is gravitomagnetism. Because vector typically they were with magnetic part. Or you can add an additional tensor, and when you go with fields Pauli gravity or massive gravity on the linearized level, but you can also go to higher level, and when you have this additional tensors which are now bi-gravity or multi-gravity, see, you can have proliferation of this tensor field, so the things become, of course, much more complicated, and you can have this tensor, vector, scalar theories. You can have everything up to spin 2 if you don't want to go higher. Or you can say what to do with the dimension of space-time, because you see, we are thought that we live in 4 dimension. Now maybe we have to think, and there's some nice ideas that maybe we live in some extra dimensions, but they are compactified. So they are these old ideas, like I showed before, Kaluza-Klein particles, and the compactifications of this extra dimensions, which could be large or it could be small. It has to be rather small because we don't see it, but they could be also warped. Or maybe we say that no, we want to go the other direction, we want to have less dimension, although we live in a four-dimensional space-time. Maybe all these things, they are just holographic, and maybe the true world is three-dimensional and we are just projection. So maybe you see you can go up and you can go down, I don't know. I will show also something about dimension later. You may also think, I want to unify with particle physics, because this was one of the parts that I told you, that's gravity and fundamental interactions. And or at the beginning Einstein tried, but he just thought, I know about QED, I don't care about weak interactions. So you see it's a bit poor, because weak interactions are there. So yes, now we can say there are some maybe grand unified fields in the particle sector when you have to couple to gravity. Actually, when you try to use supersymmetry, this unification looks better, because you can have, for example, n equal a supergravity in principle should be everything, because it has so many fields that it's everything. Or you can have other fields of very complicated groups, like E8. Another side of the unification, you can say that, for example, in quantum superstring theory, you can have both open and closed strings. And this is the one part of the gauge and one part of the gravity, which is the same like ADS-CFT duality. So one kind of unification between gravity and matter is basically say, I want ADS-CFT. And when ADS-CFT is this dual, and you can prove that this is truly dual, then you can also unify gauge and gravity and open and closed strings. This I think I said. Holography basically tells you that you want to have maybe asymptotically ADS spacetime, not just fully ADS, but maybe only asymptotically. In the case of extra dimensions, you see there are these funny names like Kaluza-Klein, who were the first, but also there is Calabi-Yau, who was later, and is very used in string theory. We can also say something about this dimension, because you see, we have the dimension of the space-time that we perceive, but this is kind of classical dimension, macroscopic dimension. We say this is 4 because there are 3 space at one time. But you see, this is a parameter of the field, so maybe it can run. Maybe you can study the flow of it. And then you can ask how is the value of this. We know how it is in IR because it's our macroscopic physics. But maybe in UV it's different. And actually there are some models, which actually here are this group of quasi-dynamical triangulation, which says that actually in UV, so very high energies, the dimension of the space-time is not 4, but it's 2. You see, you might not be sure of that, because it's a parameter of the theory. You put dimension as one of the parameters of the theory, and then it can run. So there were also some other approaches, like you see, originally with this canonical approach, there was this Wheeler-DeWitt equation, and then this was something like electrodynamics, but this was geometry dynamics, so the dynamics of geometry. But also there were some other people who say, okay, I know that you want to quantize gravity, I know that gravity is geometry, so let's study quantum geometry. So there were some people who said, okay, there is quantum geometry, which maybe look like non-commutative geometry, but then also this is a complicated topic, and when it requires advanced mathematics, you can export it also to field theory. You can study also something like non-commutative field theory, but generally these are quite complicated things, and was, for example, one of the principles which should be invoked there was some spectral action principle. So let me say that there were also some. Everything what I presented so far, this was in a continuous, that I treated gravitational field as quantized, but still continuous. Now you can say, okay, maybe it's discrete, maybe it's fractal, and we should see some atomic structure. Atomic means discrete, like atoms, they are not continuous medium. And then there were these approaches related to the Regge calculus and dynamical triangulations, which basically use this fact that we start with some finite number of points, and then we draw some lines and study evolution of surfaces, and from this we want to build the universe. So there are some approaches that you can see, maybe subjectively I can call, and this is a list of them. Okay, I will not say more about that. You see, various people do various things. They even say, okay, maybe we should abandon Lorentz relativity, and then let's do something which is only with very special conditions, only isotropic in space, and only in the special fixed point we have anisotropic scaling. This is recently famous Hořava-Lifshitz gravity. Or you can even say, okay, I don't want this Lorentzian relativity. I want something which is only with de Sitter or double special relativity, which basically tells you that now you have to rethink even classical physics. When you don't have h bar, you maybe should start with scalar relativity or de Sitter relativity, and you should describe the relativistic physics in a different way. So this is something that still is relativity, but there are also condensed matter fans. And when they say, we know you have this problem of quantum gravity, we know how to solve it. So, for example, you can use graphene, and then you can say, I know everything, because graphene is a very similar system to be relativistic, and then this kind of things is quantum gravity. Or they can say, no, there is some vacuum superfluid theory, and then they can say, I'm an expert of superfluidity, so there is a very similar structure that in gravity, so you should basically study VEC. If you study this, you will understand everything also about quantum gravity. And one of the last ideas is to say that basically, like in many condensed matter systems, this description that we use at macroscopic scale and long wavelength, this is kind of emergent, because in condensed matter we see a lot of things to be emerging from some dynamics. So maybe we see gravity on a macroscopic level, so maybe also the same should happen with quantum gravity. So, but these were just, again, theoretical approaches and theoretical problems, but we should not forget that we are physicists, so we should keep our eye on experiments, or try to look as much as possible to some experimental data, and look whether we can confirm or abandon our fears. So there are some issues which are purely theoretical, like renormalizability or UV finiteness. I showed you that Einstein-Hilbert is not good from this point of view, because this is not a normalizable theory. The other side is maybe that we have to care about the unitarity of some models. But this is, again, the theoretical issues. Now, if you want to ask whether this is something that you should be worried phenomenologically, it is, because despite the experimentalists will never tell you that, look, I made my experiment, and when I discovered that your theory is non-renormalizable. No, they will not tell you this. What they can tell you is something more intricate. Namely, they can say that I have the scattering amplitude, and then I knew that it has to satisfy some bound, but if I increase the energy, this goes above this bound. And this is something that if you take just this very naive truncation of Einstein-Hilbert happens. You see, for example, you do the, okay, not really experiment, but you can try, maybe in 100 years it will be done. You can try to do scattering of gravitons, and then this amplitude violates the bound and the energy scale, which is basically related to the Planck scale. So then you can ask the same like in the standard model. There was the question, what unitarizes the Higgs scattering? We know that actually this is done by Higgs itself. I mean, this was also for the W bosons. What unitarizes the W boson scattering in the standard model? You know, this is solved by the problem of by the Higgs particle. Here we maybe need something else, but the same problem can arise because you see, you increase the energy, you do scattering experiment, and then this is the, I would say, phenomenological question. So imagine 100 years ago, 100 years in the future, experimentalists will knock your door and say, I have this problem because the scattering experiments, the scattering amplitude violates unitarity bound. How you can solve this? So this is really the kind of problem of the phenomenological type of the quantum gravity. Or you can say, I look at the sky and then I see this problem of dark energy, dark matter, and I know I would like to extend somehow the standard model and do unification, maybe thinking still about standard model. So I think now 1 hour has passed, so this is all, and I thank you for your attention.
Thank you very much for your kind, exhaustive
Yes, yeah. I hope that you are not exhausted.
introduction to
No.
quantum gravity. And okay, so now let's open the session to questions.